Welcome back, ANPers. In today's lecture, we'll be looking at connective tissues. We'll learn the various types of connective tissue, what they're made of, their functions, and we'll even learn a little bit about the clinical relevance of one type of connective tissue using yours truly, me, as a real-life example. So stay tuned, and we'll begin shortly.
Hi, everybody.
Hi, Dr. Nick.
Hi, everybody. It's me, Dr. G. I'll be filling in for Dr. Riviera today. So let's begin. Along with epithelial tissue, muscle tissue, and nervous tissue, connective tissue is one of the 4 basic types of animal tissue. It develops from the mesoderm and is found between other tissues everywhere in the body, including in the nervous system. There are 4 main types of connective tissue. Connective tissue proper and perhaps cartilage are what most people picture when thinking about connective tissue. But there are other, less obvious types: bone and, surprisingly, blood. The major functions of connective tissue include binding or gluing tissues together, hence the name connective; support, giving cells something to sit on or in; protection, insulation, nutrient reserves, and transportation of substances throughout the body. The latter is carried out by the blood, as you might have already guessed. There are 3 things that make connective tissues different from other primary tissues. First is that they all come from mesoderm. They all have varying degrees of vascularization, or the number of blood vessels that supply nutrients to it. Cartilage is avascular, meaning it has no blood supply, but bone is highly vascularized. Finally, all the cells are suspended in an extracellular matrix, or ECM. We'll see what the ECM is made out of, but the ECM supports cells so that they can either bear weight, withstand tension, or endure abuse. All connective tissues have 3 main elements: the ground substance, protein fibers, and cells. As we'll see, the composition and arrangement of these elements vary considerably in different types of connective tissues. The ground substance is an unstructured, gel-like material that fills the spaces between cells. It's the medium through which solutes diffuse between blood, capillaries, and cells. It's composed of interstitial fluid, or ISF, cell adhesion proteins on the surface of cells that are used to attach to the connective tissue, and proteoglycans, literally meaning sugar proteins, that are made up of a protein core and large polysaccharides. Examples of proteoglycans include chondroitin sulfate and hyaluronic acid. Water is trapped in varying amounts by these proteoglycans, affecting the viscosity or fluidity of the ground substance. There are several different types of fibers in connective tissue that give it certain properties. Collagen fibers are the strongest and most abundant of the fibers in connective tissue. They have a high tensile strength, meaning they can resist pulling and shearing forces. They're made exclusively of collagen protein that forms a triple helix, as shown on the bottom of this slide. The different ways collagen is linked together makes different types of collagen fibers. Elastic fibers are networks of long, thin fibers that allow for stretch and recoil, and these are made of the protein called elastin. Finally, reticular fibers are short, fine, highly branched fibers made of collagen, but with a different chemistry and form than collagen fibers. These branching fibers form networks that offer more give than other fiber types. The ground substance and fibers together are called the extracellular matrix, or ECM. Proteins that stick out of cells or that are attached to their surfaces can be considered as ECM because technically they're outside of the plasma membrane of the cell. Connective tissue also has cells. Cells can be of two types and have different suffixes to differentiate them. Blast cells are immature forms of cells that actively secrete ground substance and ECM fibers. Fibroblasts are found in connective tissue proper. Chondroblasts are found in cartilage. Osteoblasts are found in bone, and hematopoietic stem cells in bone marrow. Cells that end in cyte, C-Y-T-E, are mature, less active forms of the blast cells. They're part of and help maintain the health of adult matrix or mature matrix. Other cell types in connective tissues include immune cells like macrophages, neutrophils, and lymphocytes, and also adipose cells or fat cells. This latter type stores cell nutrients. For each type of connective tissue that we'll cover, we'll look at the composition of the matrix and what type of fibers and cells are found within it, where it's found in the body, and what kind of functions it carries out. In addition, each slide has a photomicrograph image and a rendered drawing of the microscope image. In some slides, I've included extra diagrams and photos to beef up what the textbook has. Connective tissue proper is divided into loose and dense, and further subdivided into areolar, adipose, and reticular. Let's begin with areolar. Areolar literally means open spaces. Areolar connective tissue contains fibroblast cells that secrete a loose arrangement of mostly collagen, but some elastic fibers. This allows for increased ground substance, which can act as a reservoir of water and salts, i.e., interstitial fluid, for surrounding tissues. Almost all cells obtain their nutrients from and release their wastes into areolar connective tissue. It's the most widely distributed connective tissue and functions as a kind of universal packing material that supports and binds other tissues. It's found surrounding blood vessels, nerve bundles, muscles, and organs, and also fills the spaces between organs and forms the lamina propria, a thin layer of connective tissue that forms part of the moist linings known as mucous membranes or mucosa, which line various tubes in our body, such as the respiratory tract, the gastrointestinal tract, and the urogenital tract. Areolar connective tissue holds organs in place and attaches epithelial tissue to the underlying tissues. In addition, macrophages and fat cells are contained in the spaces provided by this type of connective tissue. We all have a love-hate relationship with adipose tissue, or as it's better known, fat. Fat is good because it is a nutrient reserve that can be liberated when food is not readily available. But too much fat makes us have to buy bigger pants, and in some cases can give rise to health issues. Adipose tissue is similar in composition to areolar tissue, but has very little matrix, which allows for greater nutrient storage because there's room for many fat-containing cells called adipocytes. The matrix separates groups of fat cells. Adipocytes are almost entirely filled with a droplet of fat, pure triglyceride, so much so that the nucleus is pushed to the very perimeter of the cell, just beneath the plasma membrane. You can see that in the image on the right, where the nucleus is stained purple. Adipose tissue's main function is energy storage, but it also functions in shock absorption and insulation. It is highly vascularized, meaning it has lots of blood vessels. Try to think about why this is the case. Adipose tissue is found all over the body, mostly under the skin, called subcutaneous fat. It is also packed around internal organs, called visceral fat, between muscles, within bone marrow, and in breast tissue. Often it's close to tissues that require a lot of energy. There are actually two types of fat, white fat and brown fat. White fat is what we just went over. Brown fat, conversely, contains both smaller droplets and high amounts of mitochondria, which give the tissue its brown color. Mitochondria use these fatty droplets to generate heat for the bloodstream. Brown adipose tissue helps newborn infants who lack the insulation provided by body hair and haven't yet learned how to shiver regulate their body temperature. It was once thought that all brown fat disappears by adulthood, but it's now known that adults do have some brown fat too. Reticular connective tissue resembles areolar tissue with a gel-like ground substance, but it only has reticular fibers and no collagen or elastic fibers. In this tissue, fibroblasts are called reticular cells. These cells secrete reticular fibers, which, if you remember, are made up of collagen protein. In reticular connective tissue, these thin fibers form a mesh-like stroma or network that acts as a support for other cells in soft organs such as the lymph nodes, kidney, spleen, bone marrow, and liver. Note that reticular fibers are found in other connective tissue types as well. So to recap, this type of connective tissue provides a soft bedding for cells to attach to and sit on. Dense connective tissue contains more collagen fibers than does loose connective tissue. As a consequence, it displays greater resistance to stretching. There are three main types of dense connective tissue: regular, irregular, and elastic. The first two differ mostly in the arrangement of collagen fibers, while the third type has an additional type of fiber to give it more elasticity. Dense, regular connective tissue consists of closely packed bundles of thick collagen fibers that run parallel to each other and parallel to the direction of pull. This arrangement of collagen fibers produces white, flexible structures with a high tensile strength that can withstand high tension and stretching in one direction. Although dense, regular connective tissue resists stretch, it can stretch a little due to the slightly wavy or crimped structure of collagen fibers, as shown in the diagram of man-made fibers at the lower right. Once the fibers straighten out, they can't stretch anymore. Between the collagen fibers are rows of fibroblasts that continuously produce collagen fibers and a small amount of ground substance. There are relatively few cells compared to the large number of fibers, and much less than in the areolar connective tissue. Dense regular connective tissue forms tendons, ligaments, and aponeuroses. Tendons are fibrous bands of dense regular connective tissue that connect muscle to bone and are able to withstand tension. Ligaments are short bands of tough, flexible, dense, regular connective tissue that connect bones together, and aponeuroses are flat, sheet-like tendons that attach muscles to other muscles or to bones. This type of connective tissue is poorly vascularized, meaning it has few blood vessels, and as a result, does not repair easily. When it does finally repair, the tissue never has the same strength as it did before injury and can more easily be re-injured. After termination of linear growth at about 17 or 18 years of age, there's very little turnover of the ECM in human tendons. A scientific study found that the half-life of collagen in mature equine or horse tendons is about 200 years. Dense irregular connective tissue contains the same elements, that is, fibers, cells, and ground substance, as dense regular tissue, but the bundles of collagen are much thicker and the direction of the fibers is random. The fibers form sheets rather than bundles. This arrangement gives the tissue greater strength in all directions and less strength in one particular direction. In some tissues, the fibers crisscross and form a mesh, while in others, stretching in several directions is achieved by alternating layers, where fibers run in the same orientation in each layer, and it's the layers themselves that are stacked at angles to one another. Dense irregular connective tissue is found in the dermis, fibrous joint capsules, the fibrous coverings of some organs, and also forms the fibrous outer layer of the perichondrium, which consists of two layers of connective tissue that closely wrap all cartilage except the cartilage in joints, which is covered by a synovial membrane. Dense, regular, elastic connective tissue is a modified version of dense, regular connective tissue that contains collagen fibers with interwoven elastic fibers. The elastic fibers allow the tissue to return to its original length after stretching. The walls of the lungs and large arteries have sheets of elastic connective tissue that allow them to stretch and recoil. Arteries need to stretch when blood enters and recoil to push the blood out. And the elastic tissue in the lungs allows them to passively return to their uninflated size after inspiration, like when you sigh after listening to me lecture for a long time. Dense, regular elastic tissue also allows certain ligaments, like those connecting adjacent vertebrae, to return to their original length after stretching. Now let's look at cartilage, which comes in three varieties: hyaline, elastic, and fibrocartilage. If you look up images of cartilage on the web, you can find a variety of products for sale, even a towel with an image of one type of cartilage that you can have for only $51. What does this image of Mylocumenia have to do with cartilage? This tiny, now extinct organism lived in the sea some 520 million years ago. Fossils of Mylocumenia have been found in the shale beds near Kunming City in China. Mylocumenia had a grisly rod made of cartilage called a notochord, the forerunner of the backbone. It's one of the earliest creatures that we know of that we can truly call a vertebrate, and so it's likely that it's the ancestor of all vertebrates, including us. Cartilage has some really interesting qualities. It's tough but flexible and resists both tension and compression. Its ground substance is about 80% water, with packed collagen fibers and proteoglycans, remember those sugar proteins, like chondroitin sulfate and hyaluronic acid. That's a tough one to pronounce. The movement of tissue fluid in its matrix allows cartilage to bounce back after being compressed and provides nutrients to the cartilage cells. Chondroblasts are the matrix-secreting cells found in developing cartilage up until the end of adolescence. In adults, mature cartilage cells called chondrocytes are found in cavities in the cartilage called lacunae. Cartilage lacks nerve fibers and is avascular, meaning it has very few or no blood vessels. It receives its nutrients and structural support from a layer of dense, irregular connective tissue that surrounds it, the perichondrium that we just talked about. Hyaline cartilage is the most abundant type of cartilage in humans. It means glass-like and is so named due to its translucent bluish-gray color. This type of cartilage contains many collagen fibers, making it quite firm. It forms the hard gristle that you find in meat. Hyaline cartilage is found at the tip of the nose, supports the respiratory passages like the trachea, forms part of the larynx, and connects the ribs to the sternum. Articular cartilage is a special name for hyaline cartilage that is found on the articular surfaces of bone, which is where bones meet and form joints. Finally, hyaline cartilage forms the embryonic skeleton before bones form. During childhood, epiphyseal plates persist in actively growing regions near the ends of the long bones. Elastic cartilage is similar to hyaline cartilage, but with more elastic fibers, which means it keeps its original shape. It forms the external part of our ears and the epiglottis, which usually prevents you from inhaling liquids or food into your trachea or windpipe. The last type of cartilage is fibrocartilage, which has properties between that of hyaline cartilage and dense regular tissue. Rows of chondrocytes alternate with rows of thick collagen fibers. This is the strongest type of cartilage because it has alternating layers of hyaline cartilage matrix and thick layers of dense collagen fibers oriented in the direction of the functional stresses. So fibrocartilage resists compression and tension, and accordingly it's found in areas such as the intervertebral discs and the meniscus of the knee, areas that are subjected to heavy pressure. Is fibrocartilage strong?
Is he strong? Listen, bud. He's got radioactive blood. Can he swing from a thread? Take a look overhead. Hey there goes the fireman.
Yes, it's strong. I want to spend a couple of minutes talking about the clinical relevance of cartilage using an injury I had about 5.5 years ago. The patient, me, presented with right knee pain for 2 months after injuring it while going down the stairs in November of the previous year. I had been running a lot before that. The patient visited the Carleton Sports Medicine Clinic and obtained a referral for an MRI, which I had late one evening in February at CHIO. As you can see at the right, there is a list of findings, only some of which are due to the injury. The rest are due to the fact that I'm old. The main finding was a torn medial meniscus with a flap and fraying of the lateral meniscus. I opted not to have surgery and allowed it to heal on its own. Cells in avascular cartilage lose the ability to divide as we age, so these types of injuries heal rather slowly. It took a couple of years before everything was back to normal, although even now it still gives me mild pain once in a while. But I can still run and work out legs at the gym. Later in life, and hopefully I'm not there yet, cartilage can calcify or ossify, becoming bony, causing chondrocytes to die. Cool fact, sharks, skates, and rays, which arose over 420 million years ago, build their skeletons entirely out of a type of ossified cartilage. That brings us to the third type of connective tissue, bone. Our skeletons, as you know, are made mostly from bone, otherwise known as osseous tissue. Bone is a living tissue composed mainly of collagen fibers and inorganic calcium phosphate. The hardness and rigidity of bone is due to the presence of this crystalline mineral salt. Bone has a hard outer layer of compact bone, but on the inside there's a spongy inner layer which is lighter and less dense. This bone matrix is organized into structural units called osteoids. An osteoid is the unmineralized organic portion of the bone matrix that forms prior to the maturation of bone tissue and is composed mainly of type 1 collagen and some non-collagenous protein. Soon after the osteoid is laid down, the inorganic calcium salts are deposited into it to form the hardened material recognized as mineralized bone. Bone has several functions. It provides structural support for the body and protection for vital organs. It also provides an environment for marrow, where blood cells are produced, and finally acts as a storage area for minerals, such as calcium, and fat. As we will learn later, bone is very important in the regulation of blood calcium levels. Cells in our bones are responsible for bone production, maintenance, and modeling. Osteoblasts produce the organic part of the matrix. Osteocytes, which reside in cavities in the bone called lacunae, maintain the bone matrix, and osteoclasts digest mineral matrix from old bone, a process that is called resorption. Unlike cartilage, bone is highly vascularized. Even in the event where a fracture is not visible on an X-ray, injury to bone can cause bleeding into joint spaces, which is called hemarthrosis, and which can be detected in an X-ray by a trained radiologist. The last and most atypical type of connective tissue is blood. Blood does not support or connect things. Rather, it functions as an internal transportation system for cells, nutrients, wastes, respiratory gases, and many other substances. Blood is classified as connective tissue because it is derived from mesenchyme and has all the components, cells, matrix, and fibers that other more familiar connective tissues have. The matrix of blood is a fluid called plasma. Blood has cells that include red blood cells, which are by far the most abundant, as well as fewer white blood cells and platelets. The fibers in blood are not readily apparent. In fact, they are normally soluble and only form after injury to blood vessels. These are the proteins that form blood clots, which we'll learn about in a later lecture. These last two slides summarize what we covered in today's lecture. The table compares the 4 different types of connective tissue and provides a succinct review of important points and might be useful as a study aid. Well, I hope you enjoyed today's lecture. I tried to make the material as interesting as possible without getting into too much detail. Information like the evolution of the backbone in ancient organisms and my old injuries are provided just to make things more interesting and won't be tested on the exam, so don't memorize them. As always, if you have questions, you can attend the live review sessions held each week and submit your questions there. Don't forget that Google provides a wealth of information too. Just be sure to use sources of material that seem, as you young folks say, legit. Remember too that these lectures can be accessed at any time and you can listen to them more than once. You can even listen to them to help you fall asleep. See you next time. Cheers.